Welcome back everyone to our calc series. Today we're going to cover properties and rules of derivatives. And the reason why this is so important is, as you've seen in our 2a video, we tried calculating the derivatives of some function. So for example, we had something like, we didn't have this exactly, but let's say we had something like this. And in order to calculate the derivative of this function, we had to run through a lot of calculations, and especially calculations for limits. So that was really complicated. And if you had to do that for every function, that would be a crazy amount of work. So properties and rules of derivatives help us to determine derivatives far more quickly. And so that is its significance. Now, properties, there are mainly four. So I'm going to label them because we're going to prove them one by one. So first of all, f and g are differentiable, and the first thing we're going to do with this is we're going to define, to prove the sum part, we're going to define, let's say L of x, because I can't use h, is equal to f of x plus g of x, right? And so this left-hand side here would just be equivalent to L prime of x, right? So you're taking the derivative of the sum of the functions. And this we can write as the limit as h approaches 0, this is the reason why I couldn't use h, Lx plus h minus Lx over h. So this is L prime of h. And because L is equal to the sum of f and g, we can write out this L using f and g. So this would be fx plus h, gx plus h minus f of x minus g of x. And we're going to put this all over h. So then what we could do is, because you can you have that the limit of a sum is equal to the sum of a limit. So recall limit of a plus b is equal to the limit of a plus the limit of b. We can similarly sort of fracture this big fraction into these green parts and these yellow parts, right? So we have f of x plus h minus h, you take the limit as h approaches 0 for this one, over h, oh sorry, this is f of x, and then you add the limit of h approaches, actually let me use a different color, plus the limit as h approaches 0 of g of x plus h minus g of x over h. So then this green part here is just simply f prime of x as per its definition. And this yellow part would become g prime of x. So this is so through this long chain here, we have that L prime of x, which is just f plus g prime, is equal to f prime of x plus g prime of x, right? So basically, if you know the derivatives of f and g, then you can find the derivative of their sum, right? Then for difference, everything is just the same. So let me show you how everything is still the same. You can use the exact same line of reasoning, but for subtraction. So we would define L as minus, and then we would go like f minus g is equal to L prime x, and then this would be the limit still here, but then here this would be minus and this would be plus, and consequently instead of this plus sign here we'd have this minus, and here we would have minus. So sum and difference are proved in the exact same way. Now for constant multiplication, what we could do is we could define L equals k times f of x. So L of x is equal to k times f of x. And so its derivative, we're going to go from right to left. So we're going to go like k times f prime is equal to L prime of x. And that would be equal to, well, you're going to do the limit as x approaches 0 of Lx plus h minus L of x over h. And then you can write L in terms of k and f. So this would just become this minus this. By properties of a limit, this k you can extract out of the limit. So this would be k times the limit as h approaches 0 of f of x plus h minus f of x over h. And this limit right over here is just the derivative of f. So that's kf prime of x. And that is exactly what we wanted to prove. So if you had a function times a constant and you want to take its whole derivative, then you can just take out the factor, or this constant factor. Then finally, the derivative of a constant, this is super easy. You can just let a function L of x be equal to k, and you can directly run this limit and you would find that it's just equal to 0. This is super easy. Now we're going to leverage one of these properties to find the derivative of x cubed plus x squared plus x plus 11 without using the definition. So what we have is we want the derivative of this expression right over here. If you put a prime after it, it just means you want the derivative of this. And so you know that this can be written as x cubed plus 2 plus x squared plus x plus 9, right? Because you want to get it to these two expressions. And so we can use the derivative of a sum. So notice this here is exactly in the form of this sum here. So basically you want the derivative of a sum, and that is equal to the sum of derivatives. So you would take the derivative of this, which we are given is 3x squared, and you would add it to the derivative of this second part, which is just 2x plus 1 as given. So we just directly leveraged this sum property, and we immediately got the answer here, right? So here we have shown how sort of useful the sum could be, but this is given that we know these smaller derivatives. And so therefore we introduce some other rules that could help us determine the derivative more quickly. So for a power function, so if you have f of x is equal to x to the nth, then its derivative is n times x n minus 1. And the way we're going to show this is, we're first going to show this for integer n. So let's say n is an integer, and we want to find f prime of x. And this is just going to be equal to the limit as h approaches 0 of, I'm going to skip writing x out, so we're going to do x plus h to the nth minus x of n over h. And then by the binomial theorem, we can expand whatever is here. So we can go like x to the n plus n choose 1 x to the n minus 1 h plus n choose 2 of x to the n minus 2 h squared, and then you would keep going until you get to n to the n h to the n. And then minus x to the n. And you would take all of this over h. So then what you could do is first of all, you could cancel these. And then you can take away, or you can cancel the h above and below. So you would get limit h approaches 0 of n choose 1 of x to the n. So notice this h would cancel with this h, and one h from each of these right over here. So you would subtract from the exponent 1 each. So this would be plus n choose 2 x to the n minus 1 2 h plus, and so on, until you get n choose n of h to the n minus 1. And then notice x is something finite, and then h would tend to 0 for all of these terms right over here. So all of these terms would vanish as h tends to 0, and this is independent from h. So this would just be equal to n choose 1 is just n, and this is x n minus 1. So this is exactly how you prove the derivative, but for AP calculus, you don't need to know this proof. So all you have to remember is just for a power function, this its derivative is just n times x to the n minus 1. So this is how you show it. You don't need to know this. And then for rational n and real n, for real n in general, that would require some later knowledge to prove. And again, the proof is not required. So you just need to know for a power function, its derivative is this. So here I would just briefly like to interject some examples. So let's say f of x is equal to this, then f prime of x we can write as first of all x to the 1/3, and then by the power rule this n is 1/3, so it's equal to n, which is 1/3 times x to the 1/3 minus 1, so that's equal to 1/3 x to the negative 2 over 3. And by the time you practice this a lot, this is going to turn very much automatic. So here we're going to have a very similar process. So f prime of x would just be equal to n, which is negative 5 over 2, and then x to the negative 3.5, or 7 over 2. Now, with this knowledge, let's try to find the derivative of this right over here. So because of the sum rule for, or like the sum property for derivatives, what we could do is we can just find the derivative of each of these individual parts. You can find the derivative of x to the 5, x to the 4th, x to the 3rd, x to the 2nd, x, and then 1. And then you can add them all up. So sort of the reasoning behind this is that you can like break these into pieces one by one. So you can go like, if I want f prime of x, right? It's f prime of this whole thing, but then that's equal to the f prime of, let's say, this plus the prime of this, and then it's the derivative of this plus the derivative of this, and you can go on. So you can just split it into each of the terms. So that's the beauty of the sum property. And so this is just equal to the derivative of x to the 5 plus the derivative of x to the 4 plus, and so on, x prime plus 1 prime. So then x to the 5, according to the power rule, is equal to 5x to the 4th. And then you can do the same thing for all the other ones. So you would go like this, this x, notice, would become, x has a power of 1, so this would become 1 times x to the 0, and that's equal to 1. And notice 1 is equal to x to the 0th, and that would be 0 times x to the negative 1. So that's equal to just, oh sorry, it's just equal to 0. Or actually, you shouldn't use the power rule for this. You can just use the derivative of a constant, right? This 1 is a constant, so therefore this 1 would vanish. So this is the derivative of this function. So notice how we skipped so much computation of limits, and we just used the power rule and the sum property and the derivative of a constant to obtain this derivative so quickly. So at this point, you should be able to compute the derivative of any polynomial pretty comfortably. And if you feel like you're not fast enough, just practice more with random polynomials, right? So in addition to polynomials, we're gonna introduce two more rules, the product and the quotient rules. And the proofs to these we're gonna put in a separate proof video because they're a little bit more complicated. And if it's just for the sake of test prep, you don't really have to know the proof, even though it's a really good thing to know. So yeah, we're just gonna focus on the product rule and take it for granted. So f times g prime is equal to, you take the derivative of the first and then you multiply it by the second original one, and then you add that to f itself times the derivative of g. So for example, if we had to find the derivative of this sort of x times y, right? So like you have two things multiplied together by expansion, then it would be quite messy because you would have 6 terms and then you would find them one by one. But what we could do instead is we could treat this as a product of these two things, and then we can take the derivative of this and then just use this expression right over here. So we can let this be f, we can let this be g, and then this would just be f prime. It's going to be f prime g plus f g. And then directly you can simplify this to obtain the derivative. Actually, in this example, it's not much more easier, but there are other examples where this would become much more necessary. So here we have 5x to the 4th, and then plus 6x squared plus 2x plus 1. Yes, good. So yeah, so that is the product rule. You can practice this by doing products like these. Just write random expressions and try to take the derivative. Then finally, we have the quotient rule. This quotient rule is just like this. It's very ugly and it's hard to use. So here we have one example. here we have this expression. Obviously, the numerator is f, the denominator is g. Then we can just take f over g prime, and that's going to be f prime, which is 3x squared, times g, minus f times g prime over the whole denominator squared. Then you can just simplify this to obtain the final result. So that is the quotient rule. And let's say we want to find the general formula for d over dx of x to the negative n. So notice this would have been covered in the power rule, right? And so sort of what we've proven here was for integer n, actually positive integer n. So n was a positive integer. And so here what we could do is sort of we prove it for the negative n's, right? So we could just use the quotient rule. So if we had x to the negative n prime, then this is equal to taking 1 over x to the n prime. And this, then we could just apply the quotient rule. So this would be f prime, 0, times whatever g is, minus f times g prime over x to the 2n. So that's just xn squared. And then simplifying this, we would obtain negative n, x to the negative n minus 1. And if you check it, you would find that this is exactly what the power rule gives us. So that is the quotient rule, and that is all the rules and properties for today. Thank you very much.